This video is going to look at, is a continuation of the last video, which was an introduction to chapter 20, and is going to look at the types of particles that a nucleus can emit and what types of decay that we have. So the first one we're going to look at is an alpha emission. So the first question becomes then, what is an alpha particle? So an alpha particle is basically a helium nucleus. So we give it the symbol 4/2 helium. It has 2 protons and 2 neutrons. And if you think about a helium atom has exactly that. It has 2 protons, 2 neutrons, and it should have 2 electrons. But because this is a helium nucleus, it has no electrons. So when we have an alpha emission, what happens is we basically take an element. Typically, this happens in heavier elements. And we're going to talk more about when this tends to happen. So just bear with me with the heavier elements. We'll define all of that in the next video. What happens with an alpha particle is basically when a nucleus gets so big and it has just so many nucleons and it's got to get rid of them as quickly and as efficiently as possible, it spits out an alpha particle because this is going to get rid of the most number of protons and neutrons that you can get rid of in one shot. The only other option would be to do fission, and we'll talk about what fission is in just a second. So let's take, for example, a 238 uranium atom, and this is going to break down via alpha emission. So when something is emitted, you're going to write it as the product. So we're going to write 4/2 helium on the right side. So if we have an alpha emission, we write whatever the particle is that emitted. Now we got to figure out what is going to be made. So if we started with U-238 and we emit a total of 2 protons and 2 neutrons, our mass number is going to go down by a total of 4. So we're going to write 234 here. And our atomic number is going to go down by a total of 2. So we're going to have something that weighs 234 atomic units and something that has 90 protons. So we go to the periodic table, we're going to look up what has 90 protons, and that's thorium. So when uranium-238 undergoes an alpha decay, it makes 234-90 thorium. And like I said, the process for doing this is if we tell you it's an alpha emission, or if you decide that it's an alpha emission, you write the particle on the side where it's being emitted, and then you just calculate what's left on the right. So the general trend for an alpha emission is that the atomic number decreases by 2, and the mass number decreases by 4. And so that's sort of a general way of going about looking at this. Now, the next one that we're going to look at is a beta emission. Okay, so a beta particle is basically an electron that comes from the nucleus. We give it the symbol 0/-1e. So this is what a beta particle is. So this is an electron, but it comes from the nucleus. It's not an electron that's in the surrounding cloud. So the reason why it gets a -1 in the atomic number spot is because that indicates that this has a -1 charge, and the E also says that it's basically an electron. So this tells us that it's an electron from the nucleus. Now, in terms of the decay, if we start with something like 14/6 carbon, and you'll notice that there's something a little odd about this carbon. The 14/6, normally carbon should be 12/6. So what this kind of is indicating is that we may have too many neutrons in this sample. So typically these tend to happen when an element has an element with too many neutrons. So we're going to find out that beta emissions actually decrease the number of neutrons. So now, again, if we decide that this is going to go by beta, we write since this is an emission, we're going to write our beta particle symbol on the other side. So just like we did in the previous example, we have to look at what's changing when we have this. So the mass number is 0. So that's easy. If the mass number change on the right is 0, if the mass number for the beta particle is 0, then we can just write 14 on top. Now, what's interesting is that we have a -1. So if we have a -1 on the right, to make this work out, then on the bottom we must have a 7 over here, because 7 minus 1 gives us back the 6 on the right. So that 7 is going to be our new atomic number, and now we can write that this is nitrogen. And if you look, this nitrogen has an equal number of protons and neutrons now. So that kind of makes sense. We've taken an element like 14/6 carbon, which has what seems like too many neutrons, and we've converted one of the neutrons to a proton. That's actually what this does. This converts a neutron to a proton. So basically the mass number remains the same, and the atomic number increases by 1. That's what a beta emission does. So now let's look at the next one. So we have what's called a positron emission. So in this case, we have to introduce what is a positron. So a positron is basically a positive electron. So it gets the symbol 0/1e. And this is what we would call a positive electron. So one thing that you have to understand is that these subatomic particles have quantum characteristics assigned to them. There are things that are called spin. There are things that are called, they have things like charm and all these other different quantum properties that are given to these subatomic particles, charge. So in nuclear reactions, what can happen is one of these subatomic particles can change its quantum characteristics to another subatomic particle, and that in and of itself can be the nuclear reaction. So a positron, being a positive electron, is nothing weird. It's just that it's a subatomic particle that has a different set of it has a different set of quantum characteristics than the electron, giving it a different charge. So what happens during a positron emission? Well, if we look at something like 30/15 phosphorus, we're going to write down our particle on the other side. So we have 0/1e as our particle. So now on the other side, we have to think about what we're going to have to write for over here. Well, again, if we have 0 on top, that's going to give us a mass number of 30 on the right. Now, on the right side, we have a +1. So since everything has to be conserved, if this were 15 on the left, then we have to have a total of 15 on the right. So this is going to give us 14 down on the bottom. So if you look that up on the periodic table, that's silicon. So the net effect of a positron emission is that we're converting a proton to a neutron. And so again, the mass number is going to stay the same because we're keeping the same number of nucleons. Okay, there we go. So it goes down by 1. So these are 3 of the 5. Now let's take a look at the next one. So the next one is what we call an electron capture. So this is the first one where it's not an emission. And it turns out that a positron emission and an electron capture have the same net effect. The only difference is that in one case, a positron is emitted, converting a neutron to a proton. In this case, with an electron capture, the nucleus picks up an electron and converts a proton to a neutron. So an electron gets the symbol 0/-1e, as we had before. So during a beta emission, we formed an electron. Now, in this case, we have the same particle, so this is 0/-1e, except the difference is that instead of instead of emitting an electron like in beta, it picks up an electron. So what happens is like, for example, if we had 82/37 rubidium, and this thing picks up an electron. So with an electron capture, we write our electron as a reactant, and now we have to figure things out. So if on the left side we have an 82 and a 0, on the right side we're also going to have an 82. Now, if on the left side we have a 37 and a -1, that means that we have to have a 36 on the right side. So if you look that up on the periodic table, that's going to be a krypton. So what happens here is an electron is captured, and it converts a proton to a neutron. So the mass number remains the same, and the atomic number is going to go down by 1. So it's basically the same. Now, we're going to just summarize positron emission and electron capture together. So what happens with positron emission and electron capture is these tend to happen in elements that have too many protons. So a beta emission is going to happen in an element that has too many neutrons. Positron emission and electron capture happen in elements with too many protons. So now let's look at the last two. And it turns out that these are actually a little bit different. So with a gamma emission and spontaneous fission, these are decay modes, but they're not due to picking up or releasing of a particular particle. So the fifth one, so this one was the fourth one, and then the fifth one is going to be a gamma emission. So gamma emission, gamma rays are basically photons. These are photons in the gamma range of the spectrum. So they represent energy, but the energy in this case is going to be equal to h nu. So they're going to have a frequency, they're going to have a wavelength, and the energy is going to be proportional to the frequency of what's emitted. So because these things don't have any kind of mass, meaning they're not a subatomic particle, when something like 99 technetium undergoes a gamma emission, we still wind up with 99 technetium, but we just get a photon that comes out and releases a small amount of energy. So in a gamma emission, there's no change in mass or atomic number. So that's gamma emission, and that's why I kind of have separated these a little bit, because these are different. So now the sixth one is spontaneous fission. So spontaneous fission is an interesting one because this is probably the most important decay mode in terms of things like nuclear fission for nuclear reactors. So in this case, what we do is a heavy nucleus splits into two lighter nuclei. So, for example, uranium-236 can break apart and can just rip apart the nucleus into two smaller pieces, where we get 96 over 39 ytterbium plus 136 over 53 iodine plus 4 neutrons plus some energy, meaning some small amount of mass in all of this is converted into energy. Overall, we still preserve the same number of nucleons, but a small amount gets converted into energy. A small amount of mass gets converted into energy, but because E equals mc squared, it turns out that energy is very large. So that's something to keep in mind and is quite important. One thing that we have to introduce is there are two other subatomic particles, and you can actually see this here. We have the neutrons and the protons. So in all of the decay modes that we covered all of the subatomic particles except for two, and those are protons and neutrons. And these are probably the two most important subatomic particles because they make up the nucleus. So the reason why I did it this way was because the spontaneous fission introduces the neutron as a possible thing that can be emitted, but we haven't covered it yet. So a proton gets the symbol 1 over 1h because, in essence, a hydrogen nucleus has one proton, so it has an atomic number of 1 and a mass number of 1. So a proton is the same thing as a hydrogen nucleus. And then a neutron gets the symbol 1 over 0 n, and that's because it has a mass number of 1 but no protons, so it gets that symbol 1 over 0 n, indicating that it's a neutron. So neutrons can be emitted in fission, just like all the other subatomic particles. And actually, this is what can cause a chain reaction. So what may have started this uranium-236 to fission was the impact of a neutron coming from another fission. So you can imagine that this chain effect, where this thing gets hit by a neutron and then it produces 4 more neutrons which can go off and hit other uranium atoms, that chain effect can lead to the fission effect, which, if it's controlled, that's how we make a nuclear reactor. If it's left to go to a full, complete chain reaction and all of the uranium atoms decompose suddenly, then you can get a nuclear explosion. So all of the energy gets, a lot of energy gets converted all at once. So this is an introduction to decay and to the different types of subatomic particles. And the next thing we're going to look at is when do these things tend to occur? When do we get these different types of decay modes?